Hello, my name is Mark Beal. I'm the president of Simmetrix, and this presentation is about the Phase 2 STTR that we have with the Navy on automated hex-dominant mesh generation. Simmetrix has been developing software related to mesh generation and geometry for computer-aided engineering for over 25 years. One thing I find personally interesting about this is the wide variety of applications of these technologies. We've developed software related to computational fluid dynamics, electromagnetics, materials modeling, structural mechanics, and also a lot of areas where multiple physics are combined into more complex simulations. I don't know if you recall the slogan from the chemical company BASF. It was, "We don't make a lot of the products you buy, we make a lot of the products you buy better." That's actually a pretty good explanation of what my company does. We license technologies to other companies that help them build better products. Mesh generation is about taking the definition of some object and breaking it up into a large number of small pieces, so the computer can solve equations on each of these small pieces and assemble those into a prediction of the overall behavior of the object. The definition of these objects might be a design in a CAD system, or might come from something like a CT scan of a manufactured part. For different kinds of physics, we need different kinds of meshes. For CFD, for example, we're modeling the air in and around some object, and we have to break the air into a mesh. For modeling structural mechanics, we have to break the definition of the mechanical component into a mesh. Another thing that's important is modifying an existing mesh, what we call mesh adaptivity. And we do this in order to meet the needs of a simulation. This might include refining the mesh to improve the solution accuracy, or modifying the mesh to account for some kind of evolving geometry during the simulation. Computer-aided engineering is used for virtually every type of manufactured product. Typically, this starts in the design process and is also used throughout the entire life cycle of the product. There are different types of meshes that are useful for different types of simulations, and our focus in this project is on hexahedral mesh generation, which can be more efficient for certain types of simulations. A hexahedral element is basically a brick, and unfortunately, the generation of these types of meshes tends to be very manual and time-consuming, because fully automatic hex meshing is still an unsolved mathematical problem. So our goal in this project is actually very simple, which is to reduce the time it takes to generate a hex-dominant mesh on complicated geometries. The goal here is to reduce this from days to weeks, down to minutes or hours, to greatly improve this part of the design process. So the approach we're taking here isn't really completely new. It's based on taking a complex shape and dividing it up into simpler shapes in which a hex mesh can be automatically created. What we're bringing to this process is utilizing multiple different types of meshing technologies, each of which can be applied to different types of geometries, and also integrating machine learning into this process to bring automation and improve the efficiency of the entire process. In this project, we're working in three main areas. One is to improve the fundamental meshing algorithms so they can be applied to more general geometries, and to improve their robustness and performance. We're developing an overall geometry decomposition procedure that's based on the needs of these individual algorithms, where one might be able to be applied in one part of the geometry, while a different one is used in a different area. We're also developing machine learning algorithms to automate this process. Now, a nice thing about this is that it's really designed to be a process where an expert can apply their expertise in critical areas and make sure they get the mesh that they need in those areas, and use the automation in less critical areas in order to improve the overall efficiency of the process. So the advantage to doing all this work is to improve the overall efficiency of the computer-aided engineering process. And as mentioned, this applies to the entire life cycle of products, from design to testing, replacing testing with simulation, and getting a better understanding of failures during the life cycle of the product, as well as determining the best ways to mitigate those failures. Increasing the efficiency of this process reduces costs at every step of the product lifecycle. Now, I mentioned that simulation is used in the design process and is also critically important in the rest of the life cycle of a product. This is very important for future developments. This can be things like evaluating the effect of damage sustained in the field and how to properly do repairs. A long-term goal is digital twin technologies, where you have a virtual representation of a system and use simulation to predict how it will behave in the future. So you can then be proactive rather than reactive in addressing things like determining inspection and maintenance intervals. These technologies can be applied in virtually every type of manufactured product, and almost every manufacturer of products uses them in some part of the life cycle of their products. The CAA market is one that's grown annually about 10%, and it's projected to continue to do that because it's a critical technology in making products more efficient. We license our software in two different ways. We license it to companies developing commercial end-user computer-aided engineering software, and we have about 3 dozen customers who do this and have tens of thousands of end users using our software. We also directly license our software to engineers and software developers at manufacturing companies, either to use directly in the design of their products or as a part of an internally developed simulation workflow that isn't addressed by available commercial products. So over the last 25 years, we have worked with a number of different organizations to help them build advanced simulation systems to solve problems that they have. This can be problems in design during the life cycle, and we are always interested in working with different organizations to see how the technologies that we have can help them meet their needs. We're also interested in working with end users to demonstrate to their existing software suppliers that our technologies can help them enhance their software and help them better meet their users' needs. If you're interested in learning more about what Simmetrix does and what technologies we offer, which are much broader than the specific things I've talked about today, I invite you to visit our website, take a look around, and feel free to contact me directly. My email address is right here. We enjoy working with different organizations who have challenging problems that they're looking for solutions to, and quite often we have a big part of those solutions already available in our software. Thank you.